Hey everyone! So let's jump right in. Today we're going to talk about something pretty wild. What if the names we have for the biggest, weirdest things in the universe, you know, dark matter, black holes, what if those names are just wrong? Not just a little bit wrong, but fundamentally misleading. We're going to explore a completely new way of talking about the cosmos, a new language that could, seriously, change how we see everything. I mean, really think about this for a second. What if dark matter isn't matter at all? And what if a black hole isn't a hole? It sounds crazy, but the words we use shape how we think. And maybe, just maybe, the names we've been using for decades are actually preventing us from seeing what's really going on out there. What if they're not just names, but mental traps? And that's really the core of it, isn't it? In physics, we often end up with these placeholders. We see an effect, like galaxies spinning way too fast, so we slap a label on the cause and call it dark matter. It's a great label for the mystery, but it doesn't actually solve it. It's like naming a ghost in your house without figuring out what's making the noise. So today, we're looking at a framework that tries to get rid of those placeholders and give these things real descriptive names based on what they might actually be. Okay, so let's get into this new cosmic dictionary. It all comes from a concept called the harmonic scale framework, or HSF for short. Now, full disclosure, this is an alternative idea. It's not textbook stuff yet. The core idea is that everything, and I mean everything, from a particle of light to a whole galaxy, is just a different vibration, a different note played on a single, fundamental cosmic string. It's a pretty mind-bending idea, but it's a powerful way to reimagine the universe. So let's swap out some of our old words. First up, the black hole. The HSF says let's stop calling it a hole. Instead, let's call it a neutrocore. And this is a huge deal. It's not just a new label. It reframes this thing from being a dead end, a cosmic vacuum cleaner, to being the engine, the active, powerful heart of the galaxy. That changes everything. All right, now for the big one, dark matter. For decades, we've been hunting for some weird, invisible particle. But what if we've been looking for the wrong thing entirely? In this new language, what we call dark matter is actually a neutral field, which the model labels K4. So get this, it's not a thing, it's a field. It's an energy field that permeates space, more like a magnetic field than a cloud of particles, a totally different way of thinking about it. And to complete our new dictionary, let's look at dark energy. You know, that mysterious force accelerating the expansion of the universe? Well, HSF calls that the cosmowave, or K5. Again, it's another fundamental energy field. So there you have it. The engine is the neutrocore, the gravitational glue is the neutrofield, and the cosmic expansion is driven by the cosmowave. A whole new set of terms for the biggest players on the cosmic stage. Okay, so we've got these new names. Neutrocore, neutrofield, cool. But why should you care? What's the point? Well, here's where it gets really interesting. Because this new language isn't just for show. It comes with a new rulebook. And the most important rule, the one that explains a ton of stuff we see in galaxies, is surprisingly simple. It all comes down to one thing, the size of the engine, how massive that central neutrocore is. That's it. That's the key. And here is that key. There's a magic number. According to this framework, there's a critical mass for these neutrocores, sitting somewhere between, say, 1 and 10 million times the mass of our sun. And this isn't just some arbitrary number. It's a fundamental tipping point. It's like a switch. If a neutrocore is below this mass, it does one thing. If it's above this mass, it does something completely different. It's a total game changer. And here's what that switch does. It's super simple. If you're a neutrocore below that critical mass, you're just not powerful enough. You can't grab onto that ambient neutral field energy that's all around you. But the moment you grow and cross that line, your ability to capture that field, that K4 energy, flips on. Suddenly you can start gathering it, accumulating it, and building that enormous energy halo that we currently call a dark matter halo. So this one simple rule creates this amazing size ladder for galaxies. Let's walk up the rungs. At the bottom, you're subcritical. You can't capture that K4 field. You don't get a stable halo. The result? Those messy, chaotic dwarf galaxies we see all over the place. Then, as you get bigger and hit that critical point, the capture mechanism switches on. You start building a halo, and that's when you see ordered, stable disks start to appear. Keep growing, go supercritical, and you build a full, stable halo, what the framework calls a neutrosphere. And that's what gives big, beautiful galaxies their stable, flat rotation curves. And finally, at the very top, the halo can actually get full, like a bucket under a faucet. It becomes oversaturated.
And when that happens, the extra K4 energy it captures has to go somewhere. So it overflows and converts into K5, the cosmowave, pushing gently outwards on everything around it. It's an entire life cycle, all driven by mass.
So we've got this beautiful, elegant little ladder. But does it actually work? Does it help us solve any real cosmic puzzles? Well, that's the true test of any new idea, right? The claim here is a big one, that this single, simple rule about mass can suddenly make sense of a whole bunch of things in astronomy that, until now, have seemed totally unrelated. It's about connecting the dots. Just look at this list. It's pretty impressive. For example, ever wonder why small dwarf galaxies are such chaotic messes with bursty star formation? Well, according to this model, it's because their little Neutrocores can't build a stable K4 halo to hold everything together. On the flip side, why do big galaxies like ours have these perfect stable rotation curves? Because their massive cores can build that halo. It even offers an explanation for why the supermassive black holes at the center of galaxies, the AGNs, seem to switch on and off. It could just be the natural cycle of the halo filling up and overflowing. See? It starts to connect things. And this idea of saturation and overflow is it's a really cool concept, especially for the biggest galaxies out there. Think about it. The halo, that big neutrosphere, it can't just grow forever. It has a limit. It's like a battery that can only hold so much charge. Once it's full, the central engine has to do something with the extra energy it keeps capturing. So it converts it. It turns the incoming K4 neutrofield into an outflow of K5 cosmowave. In other words, the biggest galaxies eventually stop hoarding dark matter and start actively, gently pushing the universe away from them. Okay, this is a really neat story. It's elegant, it connects a lot of dots. But you know what? In science, a good story is never enough. To be taken seriously, a new idea has to do more than just explain what we already know. It has to make predictions. It has to stick its neck out and say, if I'm right, here is what you should go out and find. It needs to be testable. Otherwise, it's just a fairy tale. And this framework does exactly that. It makes some really specific, concrete predictions that astronomers can actually go out and test. For example, it says, if you look at all the dwarf galaxies, they shouldn't be a smooth spectrum. There should be two different families, the chaotic little guys and the more stable ones, split right around that critical mass. It also predicts that if you plot the mass of a galaxy's core against the mass of its halo, you shouldn't get a straight line. You should see a sharp kink in the graph, right at that 10 million solar mass mark. You can even use gravitational lensing to look for the edge of a saturated halo. These aren't vague ideas. These are real, measurable things. And that's where we leave it. So what is this? Is this a genuinely new language for the universe? A better way to describe reality that finally connects all these weird, separate puzzles? Or is it just another cool story? Well, like with everything in science, the universe gets the final say. The data will decide. The great thing is, the answers are out there, waiting in the sky. We just have to keep looking, and maybe, just maybe, start asking questions in a whole new language,